Here's the coolest thing we're gonna do though. I want you to take your hand, put them out in front of you like this. Now as you're holding them right there, your left hand is a mirror image of your right hand, right? Everybody agrees with that?
Yes.
Now I want you to take your two hands and put them together so that when you look at them, you're looking at the exact same part of both hands lined up together. Now when I put them like this, I'm looking at the back of my right hand, but I'm looking at the palm of my left hand, so that doesn't work. Okay, if I look at the back of both hands, well, I can't because I'm looking at the pinky finger here, my index finger there, so I'll have to line up, that'll work. You can't line them up so they're exactly the same, can you?
No.
They're not exactly the same, Megan. So when you do them like that, you're not looking at exactly the same thing, right?
Sure.
Okay, because they're facing two different directions. Your hands are non-superimposable because you can't stack them up together. Okay? And they're mirror images of each other. So they're non-superimposable mirror images. Visual aid. Here I have two molecules in my hand. Are they the same?
Yeah.
They look the same, don't they? Okay? They're mirror images of each other. Everybody sees that? They're mirror images?
Yes.
Are they superimposable? Let's try to stack them on top of each other so they look alike. So let's start with blue and yellow. We're going to make blue and yellow in the same place. So let's see. When I make blue and yellow in the same place, what happens? Green and red don't work. Well, there's got to be some way we can do this, huh? So what do you think? Make green and red work then. Okay? If I do green and red, then what happens? Yellow and blue don't work. Okay, well, let's do something different. What about green and yellow? Well, then red and blue don't work. Then when I line two of them up, the other two don't line up. Hello. Does that make sense? So just like your hands, these two molecules are mirror images of each other. If I can get them back to that. They're mirror images of each other, but they're non-superimposable. You can't stack them together so they're exactly the same. So they are actually two different molecules, sort of. They have the same molecular formula, though, don't they? Okay, they would have the same molecular formula, but they're non-superimposable mirror images of each other. These two molecules are what is said to be that first word up there, CHIRAL. These are chiral. That word is pronounced chiral. Okay? Very important word, chiral. These are not structural isomers of each other. Remember when we did alkanes and we had the same molecular formula and we just rearranged the carbons so you still had the same number of carbons and hydrogens? Those were structural formulas. These are not structural formulas or structural isomers. These are different. These are what are called stereoisomers. And I struggled in the other class because I realized that most people in class never owned a stereo in their life.
I've seen a stereo before.
Seriously? See? How old do you feel now? How old do you feel now, huh?
They still make stereos.
Yeah, but they don't call them stereos anymore. They don't call them stereos, do
They don't call
they?
them boomboxes anymore. I mean, they're still stereo.
But you know how they explain stereo, the word stereo? When you wear headphones and you hear something different out of right and left, that's why it's called a stereo. Before they did that, it was all the same when you would listen to it. Out of both speakers came the same stuff.
That's right.
And we remember days when it was like that.
That's right.
What?
When you put your headphones on, you hear different things out of your right and left ear, right? It hasn't always been that way, people. Okay? You used to hear the same thing coming out both speakers. Okay? Think about right ear and left ear. That's why they're called stereo. Okay? Does that make sense? You're listening to it in stereo. Did y'all know that that's what it's called?
That's a term.
That's the term, right? They don't say that anymore. Do it?
You can do mono.
Yeah, it was called monaural, where it's one track. Yeah. So these are non-superimposable mirror images. They are chiral. That word, chiral, C-H-I-R-A-L, very important. We already taught about your hands. Now, if this doesn't apply to the molecules, if the molecules are superimposable, then they are achiral. Okay? So you have chiral and achiral. So the examples I use, I think, are good ones. Gloves are chiral, aren't they? Because you can't put your right hand in the left glove. Don't work.
You can, but it doesn't have those.
Yeah, it doesn't work.
Well, I hold my work glove.
If it doesn't fit, you must acquit.
So, I have to wear them.
They don't know that reference either. If it doesn't fit, you must acquit. You know what reference that is?
That reference doesn't work in my household.
That was OJ.
OJ.
That was the OJ
You can
trial.
go South Park.
Really? But a couple of things on here are achiral because they're not chiral, right? Your shoes are chiral. That's basically the definition of achiral, is they're not chiral,
That's so obvious.
right?
Little kids trying to make it.
We're more sophisticated than that. Okay. Molecules where there's a chiral carbon must have one or more chiral carbon atoms. The whole molecule can be chiral. Now here's the key to deciding if the carbon atom in a molecule is going to be chiral. Look at this carbon atom. It is bonded to 4 different things. Look at this carbon atom. It's bonded to 4 different things. It must be bonded to 4 different things in order for it to be chiral. Okay? Does that make sense? That means that it can be chiral. So let's do an example real quick. Is the carbon atom chiral?
Yes.
Yes. Bonded to 4 different things. I'm not going to put all the H's on here. I'm just going to put dashes where the H's go. All right, I'm going to number these carbons. And I will tell you that there are more than one chiral carbons on here. In this molecule, there's more than one chiral carbon. How many are there? How many chiral carbons are in that molecule? There's more than one. So let's vote. Who says there's 2? Okay. Who says there's 3? Pretty good number. Who says there's 4? You already voted.
No, I didn't.
You said there's 4?
Yeah, sure.
Who says all 5 of them are chiral? Because that's definitely not true. Okay, let's start. Let's talk about each one of them. This carbon right here and this carbon right here are kind of alike, right? They both are bonded to 3 hydrogens, so they can't be chiral because they have 3 things on this carbon that are the same. We said the rule is it has to have 4 different things on it, right? Okay. What about this carbon here? Number 2 carbon. Is it chiral?
Yes. Yes.
Yeah.
Okay, I give you that. Because this is different than that, and it has a hydrogen and a hydroxyl, right?
Are
So
you saying the right is different from the left? There's carbons on either side of that carbon.
there is a carbon, very good point. But this group over here is different than that group over there, isn't it?
Okay.
So you're looking at like the.
It's
whole-
not just the one that's adjacent to, it's the whole thing that's joined on it.
Okay.
And that's gonna be important in just a second. That's where I was trying to get to that point. Thank you for leading me into it. So this one is, what about this one over here, number 4?
It is.
Number 4 is, because it looks a lot like that one. What about number 3? Who said no? Allison, you say no? Why not?
Because it has CH2 on both sides. So it's the same. So it only has
CH2.
3 different.
Well, this stuff over here is the same as this stuff over here, isn't it?
Yeah. So it doesn't have.
This stuff here and this stuff here are exactly the same. So the answer is,
2.
no, it is not. Only 2 and 4 are chiral carbons.
But I have another question.
What do you mean? Why we need to figure this out?
I don't get why, no, I don't get why those, why you decided that.
Why I decided that?
I believe.
I'm just making crap up as I go. I really know. Sounded good, that didn't. Okay, let's just move on. since I didn't find out. No, go
So
ahead.
since they're chiral, that one can be.
No, it could be, but it's not.
It could be, but it's not.
Because, the reason it's not is because it has to be bonded to 4 different things. It's bonded to OH, it's bonded to H, so that's 2 things. But then this stuff over here, on this side here, looks exactly like this stuff here. So it's only bonded to 3 different things. Right.
Very.
You gotta look close, don't you? Yes, ma'am.
So I have another question. If you were to look at the molecule that makes up the one on the left, 1 and 2, and then compare it to 4 and 5,
Yeah.
is the hydroxyl placement going to make those different molecules?
No, because it rotates around anyway. No. They would be the same. I drew it up here like this so it was clear that they were the same. But the OH on the bottom could have been on the bottom for either one and it would have been okay.
Bless you.
I told y'all not to do that. That's just pure meanness.
Well, you still sneezed.
What do you call that? Pure meanness.
Yeah, payback.
Oh, y'all have the syphilis.
I'll get her later. So the answer to your question, no, it doesn't matter if it's on top or bottom because remember, single bonds can rotate, right?
Uh-huh.
So it could have been drawn top or bottom, it doesn't matter. It would still
So
be the
even
same.
if the hydroxyl above number 2 was moved to above to number 1.
Oh, then that's
still-
different. Then it would be different. I'm saying if it's top or bottom on 2, doesn't matter.
Okay.
If I move OH over here, then this side becomes different than that side. Yes,
Okay.
But then there would still be.
Because it's not a mirror image then.
that's right.
Okay.
Do it.
Then there would still only be 2 of the,
Then
I don't know.
yeah, then it would make this one chiral, right? Then there would still only be, no, then there would become, yeah, then there would be 2 because if you put an H up here, this one's not, then, right? Yeah. All right. Another word you may hear for these molecules that have non-superimposable mirror images is a word called stereoisomers or enantiomers. When the stereoisomers cannot be superimposed, they're called enantiomers. That's a long, fancy sounding word, isn't it? It means that they have non-superimposable mirror images of each other. Okay? It's a long word, we're not gonna deal with it a whole lot.
So they cannot be superimposed?
Non-superimposable, cannot be superimposed. Now here's an example of two that can be superimposed, right? This molecule is achiral, and automatically you should know that this molecule is achiral. Why? Because it has two bromines on it, doesn't it? It doesn't have 4 different things on it. So this molecule is achiral, okay? Tell me, look at these and tell me if these molecules are chiral or achiral. We ready? What about A? A is chiral, right? Here, look at this carbon. It has 1, 2, 3, 4 different things bonded to it. Even though, right, like her question before, this is a carbon and this is a carbon, this whole group is different than this group, right? This is an ethyl group and this is a methyl is one way to think about it. So this is chiral. What about this one? Achiral because it has 2 hydrogens on it. And C? Chiral. Clearly it has 4 different things, right?